So I want to move on, and this is all going to tie together. So let's talk about if you have a single string and it's connected on two ends. And let's imagine you really want to figure out how to make this shape on the string. That's kind of tricky to do, and you're going to do it using standing waves of the string. So it looks to me like if you were to take the fundamental mode and the second harmonic and add them together, what you're going to get is this black line right here. If you took these two waves and you were very particular in choosing the amplitudes of the waves, you can actually make it look like this black line right here, which is not such a bad representation. So it turns out, for this example, we use an amplitude where the one that's at twice the frequency. So for standing waves on a string, if you're going through the different harmonics, the frequency goes from 1 fundamental, 2 times 3 times 4, etc., as you go to higher and higher orders. So if you add these together as standing waves, and you watch the time evolution, this is what you're going to get. That's pretty cool. It's not so bad, right? So I want to give you a different way of envisioning the superposition of waves. By superposition of waves, that just means we're taking two waveforms and we're adding them together. So another way to visualize this is to look in frequency space. And what this means is you're going to plot the amplitude of the wave versus what frequency it's oscillating at. So you can see here, we use at the fundamental frequency omega 1, we had an amplitude of A. So at omega 1 on the x-axis, we go up an amplitude A. At the frequency of 2 omega, our amplitude was A divided by 2 root 2, so it wasn't as big. So that's what we're plotting here. Okay? We're going to make use of this in a minute. But, let's see. Let's imagine that you weren't quite satisfied with that waveform. You wanted to make it even closer to this weird kinked form. And so you said, let me see what happens if I add even higher harmonics. Maybe I can get this to look even better. So this particular black curve right here is drawn with these harmonics, with these particular amplitudes. Okay? Let's see what happens. Whoa. You can see it's a little closer to the pointed edge, and it looks a little closer to the pointed sawtooth-ish wave that we're trying to get. So if we look at this in frequency space, this combination of standing waves right here with the different harmonics, if you can see the amplitudes are going such as, it turns out that the 4 times omega, that one was not useful for this waveform, so it has amplitude of 0. And that the one with 5 times the frequency, we actually need to be out of phase, so it has a slightly negative amplitude. Okay. When you create sound out of a musical instrument, you are generally not just generating one frequency of sound. What you're generating is a whole bunch of different harmonics with different amplitudes. So I want to show you an example. Yes, question?
When is the fourth one? Wouldn't that mean
Yes, it means that particular. So the question is, why is the fourth wave here multiplied by 0? And it's because it has 0 amplitude in this sum. It's not contributing. It's just flat. Why is it there? Because what we're showing is a pattern here. We're showing for omega 1, 2 omega 1, 3 omega 1, etc. Because eventually we're going to expand this to the Fourier series. Yeah. So this gets me to the Fourier decomposition. So I'm going to say, so the sines and cosines, they form a complete orthonormal basis of functions, basis set of functions. What this means is that any reasonable periodic function you can write it in terms of a linear combination of sines and cosines of different frequencies. So if you have a periodic function and it has some period t or some frequency omega, for example, you can write it as a linear combination of sines and cosines that have frequencies omega, 2 omega, 3 omega, 4 omega, etc. And so let me show you with a cool visualization here. Let's see, I think actually, here we go. Ah, hold on, move my head. There we go. Okay, let me get this back over here. So what this is a really cool little applet which you can link to from the lecture slides. And what this is if we combine a whole bunch of terms, so these terms are sines and cosines. This is at omega, 2 omega, 3 omega, 4 omega, etc. This is the sine and this is the cosine. That if we sum these together, we can make these different waveforms. So if we start with a sine, well, it's pretty easy to get a sine from a combination of sines, right? So that's not incredibly exciting. Let's get something a little cooler, a triangle wave. Well, let's start off with just, all right, if we have just one term. So what this is doing is giving us one cosine term. Well, a cosine is kind of similar to a triangle wave, so that's not a bad approximation. So if I give it another term, oh, starting to look better. So now it's giving you a contribution. So this is at, looks like at 2 omega, and this is at 4 omega. We give another one, and we keep going up. It's pretty darn close to a triangle wave. Want to see some other ones? What's that? Let's go ahead and let's do a square wave. Okay. So you can see if we just put in a couple of terms, it's kind of squarish, but it's not super great. So if we add on, so remember what we're doing here is we're adding on more and more harmonics. So if we increase that number, it's getting closer and closer and closer. All right. So as you go on, it actually looks pretty darn close to a square wave. What's that? Why are they going? That's a great question. So if we consider this to be x equals 0, is this function as we've drawn it, is it an odd function or an even function? It's an odd function because if you imagine over here, it's going to be, so that means that function at x equals the negative of the function at negative x because it flips. Okay? So that means that if you were to cross x equals 0, the function over here would not be a mirror reflection. It'd be flipped around the x-axis. So that's an odd function. And so sines are odd functions, cosines are even. So you would use it as a cosine function. Let me do this thing here. Where does it say phase? I'm sorry if I'm, phase shift. Okay, let's phase shift. What this is going to do is going to take the square wave and it's going to shift it left and right. So let me phase shift this guy. Ooh, what's happening? Getting cosines. Oh! Looks like at this point we have a fully even function. It looks like it's going to be a mirror reflection about itself around x equals 0. And so now it's the same kind of amplitudes, but it's all in cosines instead of sines. Pretty cool. Do you guys want to hear what this sounds like? Yeah. Okay. If this bothers your ears, I will turn it off. Let me see. This is going to be good. Okay, so let me come over here. Where is my cursor? There we go. Okay, so let me turn sound on. Here, flip this. So that's what a square wave sounds like.
Another one.
Want to try a triangle wave?
Yeah.
So let's hear a sine wave. Okay, sine wave is at a single frequency, right? We can see that right here. If you look at a triangle wave, it doesn't sound terribly different from the sine wave because it's really pretty darn close to being, remember we phase shifted, so that's why we're not cosines. It's really close to being a single frequency. If we look at a square wave, like we've got all these different frequencies contributing.